Page 469, section 7.5 is inverse trig functions. If we want to look today at the derivatives of inverse trig functions, probably a good idea to remember what inverse trig functions are themselves before we start trying to find the derivatives. So we're going to do a lot of pre-cal review before we get into some calculus today. If you want to find the inverse and determine whether the inverse is a function or not. Remember back in the beginning of chapter 7 we talked about horizontal and vertical line tests, right? And we said that if something passes a vertical line test, then that means it is a function, so the sine curve would be a function. But if its inverse is going to be a function so that it's a one-to-one function, it would also have to pass the horizontal line test. And you can see the trig that most trig functions, including sine here, are going to fail that miserably. If I draw a horizontal line, I'm going to hit that graph in more than one spot. So for that reason, you'll remember from last year, we limited the inverse trig functions to particular regions. And the region designated for inverse sine is going to be from negative pi over 2 to positive pi over 2, because you can see on the regular sine curve that would pass a horizontal and a vertical line test if we just looked at that region. So when we are working with inverse sine, our range is going to be from negative pi over 2 to positive pi over 2, since that's the domain of the regular sine. It is the range of the inverse sine, because domain and range switch places. And if you think about it on the regular sine curve, it oscillates between 1 and negative 1 for the range, so that's going to be the domain of the inverse between 1 and negative 1. If we restrict inverse sine to be just the region from negative pi over 2 to positive pi over 2, if you think about that on the unit circle, if you go up to pi over 2 and you go down to negative pi over 2, that's like the first and the fourth quadrants, right? And so that's another way to think of this, that for inverse sine we're going to use first and fourth quadrants. In the first quadrant, sine's positive, and in the fourth it's negative, so it'll make it very clear to us which of those that we are working with. The two ways that we'll denote inverse sine so that it's very clear to us what they want us to do is we can write it this way, like sine to the negative 1, that's read inverse sine of x equals y, or arc sine x is equal to y. And in both cases, that means the sine of y is equal to x. We joked last year that those were our Jeopardy questions. It's like they're giving me the answer and they want to know the question. It's like they're saying the sine is equal to 1/2, so what was the angle that I had to begin with that when I took the sine of it, it gave me 1/2. So we're going backwards, thus the idea of an inverse. So for example number 1, they ask us to find the inverse sine of a negative 1/2. So by definition that we were just talking about up here, when I see inverse sine of negative 1/2 is equal to what? That means that the sine of y is equal to negative 1/2, and I only have first and fourth to choose from. So the sine of y is equal to negative 1/2, and I only have first and fourth to choose from. I get all of that from my definition. Since this is a negative 1/2, then I automatically know that I'm in the fourth quadrant, because positive in the first, negative in the fourth. And I need to find a reference angle. So I can say, okay, where is sine typically equal to 1/2? In the first quadrant, sine's equal to 1/2 at pi over 6. That's my reference angle. And so then I can say, okay, what's the fourth quadrant? Pi over 6. And the fourth quadrant, pi over 6, would be negative pi over 6. Now, that's the same thing as negative pi over 6 is the same thing as 11 pi over 6. They're coterminals. If you add 2 pi to the first one, you get the second one. If you subtract 2 pi from the second one, you get the first one. They're coterminals. However, we want to write that as negative pi over 6 as opposed to 11 pi over 6. The reason for that is, again, look at your range. Your range says that the answers that you're giving for y should be in between negative pi over 2 and positive pi over 2. Negative pi over 6 is. 11 pi over 6 is not. So that's going to be our preferred answer. All right, look at the second one. The second one, we've got the tangent of the arc sine of 1/3. By definition, that means that sine is equal to 1/3, and I have first and fourth to choose from. So when I have two things going on, I'm going to start on the inside, work my way out. Order of operations, start with those parentheses. So I'm going to focus on my inverse sine. I don't know where sine is equal to 1/3. That's not a value that we have memorized off of the unit circle. So instead, I'm going to build a triangle. So I can say, okay, If sine is equal to opposite over hypotenuse, then I can do opposite 1 over hypotenuse 3. And I can do Pythagorean Theorem to figure out my other side. When I do Pythagorean Theorem, though, I'm going to get either a positive or a negative 2 square roots of 2. And I don't know which one it is. It depends on the quadrant that I'm in. So I can go back and say, okay, if I only had first and fourth to choose from, and this was a positive 1/3, I had to be in the first quadrant. If this had been a negative 1/3, I would have been in the fourth quadrant. So if I'm in the first quadrant, I'm going to choose the positive 2 square roots of 2 as this other side. So there are two things that I have to get from that inside piece of information right there. I have to get the values of my triangle, and I have to get what quadrant I'm in. Once I've gotten that, then I can say, okay, what did the problem actually ask me to find? It actually asked me to find the tangent based on that information. So what's the tangent of y? So I can come over here and say tangent is going to be opposite over adjacent. So that's going to be 1 over the positive 2 square roots of 2. And then, of course, we would rationalize our answer to be square root of 2 over 4. Now, remember that when we talked about inverses, we talked about cancellation equations. We said that if you take a function of its inverse or an inverse of its function, they'll cancel each other out, undo each other, right? So there are some times when I do a composition of a function and its inverse, they undo each other, they cancel each other out. Back here we had a composition, but it was not of a function and its inverse. It wasn't tangent and arctangent or sine and arcsine. But down here I do have a function and its inverse. I have sine of inverse sine, and here I have inverse sine of sine. So those cancel each other out and take me straight to my answer of 0.6, straight to my answer of pi over 12. You might remember, though, that there was a catch to those cancellation equations. And we see that in example 2c. If I try to do the inverse sine of the sine of 2 pi over 3 by canceling, I'm left with an answer of 2 pi over 3. What's wrong with that? It's not in my range, right? It's not in that designated region of negative pi over 2 to positive pi over 2. That has to be first and fourth, and this is in the second. So I can't get an answer in a region that doesn't exist. So that means I'm going to have to do this problem differently. I'm going to need to go back to my original and treat it the exact same way we did this guy back here. Start on the inside, simplify that down, and then work our way to the outside. So first I need to figure out what the sine of 2 pi over 3 is. The way that we did that, if you didn't want to build the whole unit circle just to get one value and you didn't have a calculator, was we said step number 1, we're going to find the sine of the reference angle because the values in the first quadrant just reflect around to the other 3 quadrants. So we could say the sine at pi over 3, and that would give us our value of square root of 3 over 2. Then the only thing I have to figure out is if it's positive or negative based on the quadrant that it's in. We've already established 2 pi over 3 is in the second quadrant. So in the second quadrant, all students take calculus. Students means sine is positive. So I'm going to be positive in the second quadrant, so I can have a positive square root of 3 over 2 there. So let's replace sine 2 pi over 3 with positive square root of 3 over 2. So now I have inverse sine of square root of 3 over 2. By definition, that means that sine y is equal to square root of 3 over 2, and I only have first and fourth quadrants to choose from. Since this was a positive square root of 3 over 2, I have to be in the first quadrant. If it had been negative, I would have been in the fourth. So I can say, where is sine equal to square root of 3 over 2 in the first quadrant? Pi over 3, right? And that'll be my answer. So you can see if I had gone with the 2 pi over 3, it would not have been correct. So all of that, a review of what an inverse trig function is, so that then we can see how to take the derivative of an inverse trig function. So on the top of page 471, they tell me, we know that the sine function f is continuous, so the inverse sine function is also continuous. If you can draw something without picking up your pen or pencil, when you reflect it across the line y equals x, you'll still be able to draw it without picking up your pen or pencil, right? So that makes sense. It says we also know from section 3.5 that the sine function is differentiable, so the inverse sine function is also going to be differentiable. So, that's important when anytime we start a formula, it typically starts off with if the function is continuous and differentiable, then type of thing. So that will help us in the future when we're looking at inverse sine continuity and differentiability. All right, so what's the formula then for the derivative of inverse sine? It is 1 over the square root of 1 minus x squared. Now, if I have the square root of 1 minus x squared in the denominator, we're going to have some restrictions there, right? Can't get 0 in the denominator, can't get a negative under the square root. And so that's why we have the restriction that x has to be between -1 and 1. That's the only place that that function would exist. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. Where does that come from? Well, the proof for that derivative, fairly straightforward. If I'm talking about the derivative of inverse sine, remember we said by definition that inverse sine x equals y means that sine y is equal to x, right? So if I want to prove the derivative of sine y is equal to x, is this guy right here, I'm going to go through and I'm going to take the derivative on both sides. So this is the derivative in terms of x. So the derivative of sine is cosine. And since that was not in terms of y, I have to leave a dy dx in there with my implicit differentiation. Over here, derivative of x is equal to 1. So to get dy dx by itself, I'll divide both sides by that cosine y, so I'll have my derivative as 1 over cosine y. This is supposed to be the derivative in terms of x. That is not in terms of x. So I got to replace y with an x. So I could come over here and do exactly what we were doing just a second ago. We started off with sine y equals x. So if sine y equals x, that means sine is equal to x over 1, opposite over hypotenuse, Pythagorean Theorem to get the other side. And because it was positive, I'll be in the first quadrant, so that would be a positive radical on the other side. So I'm trying to figure out what cosine y is, right? So I can say cosine is adjacent over hypotenuse, so that would be the radical over 1. And so we could replace cosine y with what it's equal to, that radical. Another way that you could figure out what cosine y was is you could use your Pythagorean identity. Cosine squared plus sine squared is equal to 1, and solve it for cosine y. So if I were solving this for cosine, I subtract the sine squared from both sides and take the square root of both sides. And this sine y, remember sine y was equal to x. So if this is sine y squared, that would be the same thing as x squared. That'd be another way that you could get that cosine y was equal to the square root of 1 minus x squared. So that's where our formula comes from. That's the proof of it, of where we get it. So now let's use it. Example number 3, we've got f of x is equal to the inverse sine of x squared minus 1. So we have our formula up here. We're going to have a quantity down here. So let's go through and take the derivative, then we'll come back and talk about these domain ideas. All right, so if I'm going to take the derivative of the inverse sine of x, according to my formula, that's 1 over the square root of 1 minus x squared, I have a u in here. So I'm going to do some u substitution. I'm going to replace x with x squared minus 1. That's my u value, x squared minus 1. So if it was x squared, I'm going to have x squared minus 1 squared. And of course, anytime we use u substitution, we have to use chain rule. So we have to multiply by the derivative of u. So the derivative of x squared minus 1 is going to be 2x. To simplify that, I can see that negative 1 squared is going to be positive 1, and that if I distributed that negative, I'd be able to cancel the 1's there. So we don't always FOIL and expand and that type of thing, but I am going to on this one because I can see I'll be able to simplify it if I do. So if I go through and take x squared minus 1 and I square it, that's where we're getting the x to the 4th, 2x squared, and 1. We had a negative out in front, so it changed every one of their signs. So then, yeah, that 1 and negative 1 will drop out and leave me with just the 2x squared minus x to the 4th. That has a common factor of x squared. So if I have the square root of x squared, that's x, right? So that would cancel with the x in the numerator. So I'm going to take out that common factor, and you can go ahead and do the square root of x squared is x before you cancel, or you can go ahead and cancel it here. Either way. And so we'll be left with 2 over our simplified radical. And if you wanted to rationalize it and get that radical out of the bottom, you could. It's really just an issue of matching the answer in the back of the book or matching the answer on the multiple choice on AP as to how far we have to go with our simplification. All right, so let's talk about these domains. In example 3, they asked me to find the domain of the original function, and they asked me to find the domain of the derivative. So let's start with the domain of the original function. In the original function, our domain has to be an x value in between -1 and +1. So if it's going to be in between -1 and +1, whatever we're taking the derivative of, whatever we're taking the inverse sine of, in this case it was x squared minus 1, whatever that is has to be in between -1 and 1. So let's put our x squared minus 1 in there between -1 and 1. So I'm going to add 1 to both sides. That would give me 0 is less than or equal to x squared is less than or equal to 2, and take the square root of both sides. So square root of 0 is 0, square root of 2 is square root of 2, and the square root of x squared is the absolute value of x. That's why we always have to put in the plus or minus. We learned that earlier this year. So now I have an absolute value inequality, and I actually have a combined inequality. So I could break that into 2 separate pieces if I want to solve that. And so over here, I'm going to have whatever I have in the absolute value, take it out, copy the same sign, copy the opposite number. Same idea over here, whatever I have in the absolute value, take it out, copy the same sign, copy the opposite number, right? So for this piece, we're going to have x as the values in between negative square root of 2 and positive square root of 2. Over here, this is actually a disjunction that we could write as 2 separate pieces, but there was really no need if we're looking at in the very beginning, this was where all of these things existed at one time. This guy is going to be x is greater than or equal to 0 or x is less than or equal to 0. That's going to be all real numbers, right? So where that would overlap with this answer over here would just be that same answer over there. So it's already included in my final answer. So there is our domain for our original function. How do I find the domain for the derivative? The domain for the derivative is probably easiest to find by actually looking at the answer that you get for the derivative. Because the derivative is going to exist anywhere I don't have 0 in the denominator or a negative under the radical. So that's probably the easiest way to establish its domain. Don't forget, though, that when you look at it, you have to look at what you had before you simplified. Just because something canceled out doesn't mean it wasn't there originally, and it would have still caused a problem of a 0 in the denominator or a negative under a square root. So when I want to establish the domain for my derivative, I'm going to go back and say the only restriction would be I can't get a 0 in this denominator, and I can't get a negative under this radical. So what was under the radical, 2x squared minus x to the 4th, has to be greater than 0 to avoid those 2 problems. That is a polynomial inequality. We did those in August, maybe. We've seen them several times since then, but good review for us. So I'm going to take out a common factor of x squared. And then remember that we treat this as if it said equal to. So I'm going to set x squared equal to 0, and I'll get x equals 0 as a double root. I'm going to set 2 minus x squared equal to 0, and I'll get x is equal to plus or minus the square root of 3. Those are my critical numbers. I'm going to put those on a sine graph. So I'll come down here. I have a double root at 0. It's important to remember that's a double root. Single root at negative square root of 2 and at square root of 2. All right, so to make my sine graph, I'm going to pick a test point. Positive 1 would probably be an easy thing to choose and to plug in here. So I'll get 2 minus 1, which is 1. So positive there. Cross a single critical number, the sign changes. Cross a double root, a double critical number, the sign changes twice, so it appears to not change at all. And then cross the single critical number, and the sign changes. So there's our sine graph. And they were asking us for where is this thing greater than 0, meaning where is it positive. So that would be the piece from negative square root of 2 to 0, and the piece from 0 to square root of 2. I do have to leave 0 out of that. So again, the key focus for this section is taking the derivatives of the inverse trig functions, but we do get some really good review here in practice with finding domains, and we have to do domains and ranges all the time, so it's good review for us. All right, once I understand inverse trig functions and their derivatives for sine, then it's much simpler to look at it for cosine and tangent as well. So let's talk about cosine. Here's the graph of my cosine curve. Again, you can see it's going to miserably fail a horizontal line test, so I'm going to need a restricted region. And so you'll remember from pre-cal, the region that we use is from 0 to pi. If I'm looking at 0 to pi, that's the first and the second quadrants. And again, cosine's positive in the first and negative in the second, so we'll be able to tell what quadrant we're in. Exact same notation that we had before. If this is y equals cosine x, then its inverse should be x equals cosine y, and we represent that with inverse cosine x equals y, or arc cosine x is equal to y. Again, that range restriction that we talked about a moment ago, and of course domain still going from -1 to +1, since that's originally the range of the regular cosine curve. The derivative of inverse cosine is going to be a negative of the exact same formula we had for the derivative of inverse sine. That's really cool, right? Because the derivative of cosine is typically negative sine. That's exactly what we have here, right? The derivative of inverse cosine is a negative of what we had for the derivative of inverse sine. So that makes it pretty easy to keep straight. All right, what about tangent? If I were looking at the tangent curve, it also would fail the horizontal line test. And so I would need a restricted region, and that region is from -pi/2 to +pi/2. So that is the first and the fourth quadrants. So sine and tangent use first and fourth. Cosine uses first and second. There is a slight difference between the range when we're working with inverse tangent as opposed to inverse sine. Notice we don't have equal to here because the inverse is undefined there because we have asymptotes there. So it's equal to with sine but not with tangent. And as we just alluded to, we do have horizontal asymptotes at y equals pi/2 and y equals -pi/2. That'll help us with our limits in just a minute. And then the derivative of inverse tangent is going to be 1 over 1 plus x squared. There are derivatives of the other three trig functions as well, but remember that we use tangent, sine, and cosine more often than secant, cosecant, and cotangent, and that'll be the case with their inverses and their derivatives as well. So look at example 4. We've already worked with inverse sine, but we haven't done anything with inverse cosine and inverse tangent. So let's just do a normal problem that involves those before we get into their derivatives. So here's a composition where we have cosine and inverse tangent. I can't cancel because they're not the same. It's not cosine of inverse cosine or tangent of inverse tangent. So I'm going to start on the inside of this composition and say inverse tangent of -x means tangent y equals -x, and I only have first and fourth to choose from. I get all that from its definition that we were just talking about right back here. Because this is a -x, I have to be in the fourth quadrant. If it had been positive, I would have been in the first. And I can come build a triangle. So I can say if tangent is -x over 1, then I can say opposite over adjacent, -x over 1. Since I've established them in the fourth quadrant, that's how I know it's the x that's negative and the 1 that's positive. And then Pythagorean Theorem to get the other side. And that's a radius or a hypotenuse, so it's always positive. So from that inside piece of information, we have to get our triangle values and the quadrant we're in. We've got that, so now we can answer the question that was asked, what is the cosine? So I can look at this and say cosine is adjacent over hypotenuse. And so that would give us 1 over the radical, and we could rationalize to get our final answer. They give me a couple of limit laws on the top of page 473 that deal with inverse tangent. This is what the graph of inverse tangent looks like. We could generate that if we wanted to by taking the graph of our regular tangent curve and reflecting it in that line y equals x. We could generate our inverse tangent. But looking at inverse tangent, you see where these limit laws come from. They tell me the limit as x approaches infinity of inverse tangent will be pi over 2. And so sure enough, as x goes off to infinity, you can see that approaching pi over 2. And then the limit as x approaches a negative infinity for inverse tangent goes to negative pi over 2. And again, we can see that down here as well. We also can get it from, remember the definition of a horizontal asymptote is you have to be able to take a limit of infinity and get one of those two as your answer to be able to have a horizontal asymptote. So that follows suit for us as well and makes sense. So then we can use those limit laws to help us do something like example number 5. For example number 5, we've got the limit as x approaches 2 from the right of the arctangent of 1 over x minus 2. I don't even know where to begin with that. This craziness right here is what's causing me grief. So I'm going to substitute that out. I'm going to let 1 over x minus 2 be u. So then that would give me arctan u. That's a little easier to deal with. If I'm going to replace this x with a u, I also have to replace this x with a u. So I need to figure out what is u approaching as x is approaching 2 from the right. So if I'm putting in values approaching 2 from the right, that's like 2.1, 2.01, 2.001, right? So as I plug those in, 2.1 would give me 0.1. 2.01 would give me 0.01. 2.001 would give me 0.001. Numerator staying the same, denominator getting smaller and smaller and smaller, what does the overall fraction do? Get bigger and bigger, right? And so u would go to infinity. So now I've rewritten this, and it is a perfect match for that limit law that we just talked about a moment ago. And so that could take me straight to my answer of pi over 2. All right, so what about derivatives of inverse cosine and inverse tangent? We've got the rule right here for inverse cosine and for inverse tangent. So let's see how we could use those. They're also going to give me the other 3 inverse trig derivatives, and as we mentioned, we don't use those as often, but we do have them there. So example 6, they give me 1 over inverse sine of x, and they ask me to find the derivative. So to begin with, I don't want to have to do a quotient rule. I'm going to rewrite that by moving it up to the top with a negative exponent so I can use power rule instead. So right now I have a quantity. I'm going to call this u. I have a quantity to the negative 1. So if I have u to the negative 1, then I can go through and say no matter what that quantity is, that would be negative 1 u to the negative 2. Negative 1 u to the negative 2. And then I need to multiply by the derivative of u, right? That's my chain rule. Derivative of outside times derivative of inside. So my u was inverse sine of x. So I'm going to use that new formula that we learned today. The new formula that we learned was 1 over the square root of 1 minus x squared. So derivative of outside times derivative of inside. So one more time, we thought of this as u, and we said if this is u to the negative 1, that would be negative 1 u to the negative 2. We don't change this at all, we just bring it along. Then we need to multiply it by the derivative of u. And if u was inverse sine, that's that new formula that we proved earlier today, 1 over the square root of 1 minus x squared. All right, so let's simplify a little bit. We've got negative 1 times 1 in the top. We can move this guy back down to the bottom to get rid of that negative exponent. And if we're not allowed to leave a radical in the denominator, then we would rationalize. Of course, on the FRQs, they don't care if you simplify or rationalize. On the multiple choice, they probably would require you to. So again, just an issue of trying to match the answer choices that we're provided with. All right, look at the next one. For the next one, we have a product, right? We've got x times inverse tangent of square root of x. So I'm going to have to use my product rule. First times derivative of second plus second times derivative of first, right? So if we do first times derivative of second, Again, this is inverse tangent of square root of x, or x to the 1/2. Whichever way you think of it, that's still a quantity. I'm going to need to use some u substitution. So I'm looking at first times derivative of second. So if I have inverse tangent of u, that would be, according to the formula we learned a second ago, 1 over 1 plus u squared. So the formula we had for the derivative of inverse tangent is 1 over 1 plus u squared. Since our u is x to the 1/2, or square root of x, then I can say square root of x squared. That's the derivative of the outside. We have to use chain rule. We have to do derivative of the inside, right? So I need the derivative of x to the 1/2. That just gets really crazy confusing over here to me. So I'm going to come out here to the side and think for just a second, what would the derivative of x to the 1/2 be? Well, that would be 1/2 x to the negative 1/2. And I could move that x to the negative 1/2 down to the bottom to get rid of that negative exponent. And once I've got that, then I can bring it back over here. So this was first. This whole thing is derivative of the second, where this is chain rule, derivative of the outside times derivative of the inside. All right, then second times derivative of first. Derivative of x is a little bit easier to contend with, just 1. And now I just need to simplify a little bit. So if I had the square root of x squared, that would just give me x. Then this is x divided by x to the 1/2. When your bases are the same and you're dividing, you subtract your exponents, right? So x to the 1 divided by x to the 1/2 would just leave me x to the 1/2, or square root of x, however you'd prefer to write it. We still have this 2 in the bottom, so we could take that 2 and multiply it by the 1 plus x, so that would give us 2 plus 2x. And that's about as simplified as we can make that. All right, so here is our homework for tonight. Be sure on number 23 you notice that the answer in the back of the book is wrong. I don't want you working the problem repeatedly and then find out that you did it right the first time and the book was wrong. So please be sure that you get that correction as well.